degree 4 Taylor polynomial that you were finding centered at pi over 2. And so what I wanted to do was go ahead and give you the answer, and then also we'll just go ahead and take a look at the Desmos worksheet. So if we go back there, in fact, before we look at that particular function, we'll just go back and look at the Taylor polynomial that we computed in the example before of e to the x. And since that's the one that the Desmos worksheet works with by default, so here's e to the x. I'm going to go ahead and bump this up, the degree 1 Taylor polynomial. And now here, a is the base point. So we can just adjust a until we see a equals 1. And then what we've got here, if you look on the graph, there's the point. There's the point on the graph where x equals 1. You can see that y is equal to e. And then the line that we have there is the tangent line. What we calculated that to be was, if you recall, just p1 of x was equal to ex. So there was no constant term. And here you can see that indeed this red line does go through the origin right at 0. So there's the best degree 1 polynomial is what we calculated. Now if we go back here and increase this to 2, right? Now, oops, I'm sorry, we didn't want to increase a to 2. We're leaving a at 1. We're increasing the degree to 2. Now we see the best polynomial centered at 0e. And so that is exactly this this red parabola here that we've computed, and this is the one that we had the formula for. So you can see here that there is a constant term because that red parabola doesn't go through the origin, and we could even go here and describe. Let's see if I can get that point to show up. That is 1.359. So I'm going to go ahead and head back here. 1.359 is approximately, of course these are decimal approximations, e over 2, right? And so what you should be seeing here is that the formulas we derived are what we saw in the graph in the Desmos worksheet. You can do the same thing with the Taylor polynomial for sine of x. So we're going to go ahead and do that. We'll get the degree 4 Taylor polynomial. So back here, let's change this function. All right, so here's sine of x. Let's go ahead and our a was supposed to be, let's see, it was supposed to be pi over 2. A equals, let's see if we can get pi. Pi over 2. All right, so there we go. So there's our a, and what you can see is, okay, so here's pi over 2 right there. And what you can see is that the degree 1 approximation is actually just the function that is a constant height of 1. The degree 2 polynomial is going to be the parabola that's shown here. Degree 3, it's still that same parabola. Again, the function is symmetric about the base point, and so we're only getting even contributions. And here we see the best degree 4 approximation, and you can see if we compare this to the degree 2 approximation that it's hugging the curve for a larger amount of the graph. so the additional wiggles with a degree 4 polynomial allow the polynomial to wiggle more with the sine function, right? And of course, as I would bump this up, as we go up by 2's, right, you can see the function hugging the graph better and better. So what we calculated here is the degree 4 polynomial. The last thing I'll comment about this exercise is that you'll notice the similarity between this polynomial so this looks similar to the degree 4 polynomial for cosine. It looks similar. In particular, this is the degree 4 polynomial for cosine, except it has been shifted. This Taylor polynomial is shifted by pi over 2 to the right. And I'll just comment that that's not an accident, because as you know, sine of x is cosine of x shifted by pi over 2 to the right. So this is because sine x is equal to cosine of x minus pi over 2. All right, so again, I'd like to see the calculations that you used to get this result. I think going through those calculations is good to be able to do, and reinforces what's going on with the formulas. All right, so now I want to move into thinking, and we know that we can increase the accuracy or increase the degree of the Taylor polynomials, and the goal is to get a more and more accurate approximation of our function. So we are matching more higher and higher order derivatives to our function, and so as I mentioned before. Each successive Taylor polynomial is just adding higher order terms. So let me switch colors here. So the degree k plus 1 Taylor polynomial for a function f centered at x equals a. So the Taylor polynomial we're denoting as p sub k plus 1 of x for a function f centered at x equals a is actually equal to well, we have a formula, right? So our formula, and I just want to remind you, our formula is this one right here that I've got in orange. Notice that if I'm considering these terms here, this is really the same as the kth Taylor polynomial plus the last term, right? And so what is that last term? It's f k plus 1 evaluated at a over k plus 1 factorial times x minus a to the k plus 1. So what we're seeing here then is that each Taylor polynomial is successively adding onto the next, right? And so here we can say Pn of x in summation form is just equal to the sum from k equals 0 to infinity sorry, not 0 to infinity, 0 to n. I'm getting a little bit ahead of myself. So we have the finite, that each one of these is a finite sum. And so what you might be thinking is, well, can we, it's sort of the interesting extension of what we've been thinking about that I hinted at the end of the first video, is that we might like to think about summing up infinitely many functions. So what if we sum from 0 to infinity, right? And so so let's consider k equals 0 to infinity, this quantity. All right, and so this quantity is defined to be the Taylor series for f centered at x equals a. I'm going to go ahead and add another page here. And so, whoops, some of that got moved down to the next page. So let's go ahead and centered at x equals a. So, okay, so now we have a definition, and what we're thinking about is that this particular infinite sum, we can think about it as is the limit of finite sums. Of polynomials. And so in preview activity, .3.1, what you did is you looked at the Taylor series, right? So you looked at the set of Taylor approximations of e to the x, and you found that the points on the graphs of the Taylor polynomials were converging to the number e. Right, so let me go ahead and sketch what I'm saying here. So we have this function e to the x, right? And this is at 1, this has height e. So what you were doing in that preview activity is you were considering the set of points that, and I think actually this so here's P2 of x, and here's P1 of x. And so what we did in this preview activity is you looked at the sequence of points right, on these successive polynomials evaluated at 1, and we considered the fact that those are converging to, that's a convergent sequence of numbers whose limit is e, right? So what we said was the limit as k approaches infinity of pk of 1 is equal to e. This is what that preview activity did. And here pk of x is equal to the kth Taylor polynomial of e to the x centered at x equals 0. And so this is kind of bringing up a point here, a question that you might have, which is, I have this sequence of Taylor polynomials. So it's and the sequence of Taylor polynomials is the sequence of partial sums of the Taylor series. So let me go ahead and write that down. That's an important fact. The sequence of Taylor polynomials is the sequence of partial sums of the associated Taylor series. Okay, and so what we might ask is, for which points or which real numbers, so question, for which numbers, let's go ahead and put a number in here. Let's just call this, for which numbers b is it the case that the limit as k goes to infinity, pk of b converges. Okay, and pictorially here what we're saying is, if I take the set of red approximating Taylor polynomials, for which points is it the case that that the green points will actually converge? And of course, if they converge, we would like those to converge to the original function. But we're going to go ahead and first just ask the question, when do they converge? And the answer is actually kind of interesting. I want to go ahead and stop this video here, and I'm going to resume with another video because of the limitations of Desmos. It turns out that Desmos isn't as good for visualizing this. So I'm going to stop here and we'll resume with another video where I show you a demo of this idea, these functions converging. So let me go ahead and stop this and resume with the next video. There's not a your turn between this and the next video, so you can move directly on or take a break as you like.